Hypothalamus Artificial Intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the short conference. Sparse Analytics and Artificial Brains. Conference prepared and edited by Jesus Velasquez Bermudez. His resume may be found on LinkedIn. The new way of mathematics is directly related to the parallel thinking, and today it can be said that like paper-based math, sequential mathematics for single-processor computers will be in the short term a dead language. As in the human brain, in the future only parallel mathematical thinking will be practical. The new analytics is autonomous, parallel, and distributed. Sparse analytics, or parallel and distributed analytics, is the methodological basis of artificial brains. There are two approaches to process data from a super-measurement system that provides a non-enumerating amount of data, in real time and asynchronously: parallel analytics and distributed analytics. These two terms seem to be the same, but they are different and complementary terms. The parallelism and distribution of computing processing goes beyond the simple construction of parallel mathematical algorithms. It implies a way of facing problems with the bottom-up approach, from the description of atoms to integrating the vision of the entire system. It is a way of thinking about mathematics, according to the development of computer technologies. This is consistent with the abolition of monolithic computer applications, to make way for distributed applications based on microservices. Then the next step of advanced analytics is sparse analytics, which is based on parallel and distributed analytics. Asynchronous parallel analytics, called asynchronous parallel optimization by Velasquez, in 1995, 1997, and 1998, is defined as the act of solving a mathematical problem, using multiple cores on a computer, or on a computer grid, using modern multiprocessing environments, uniting the theories of decomposition and partition of large systems, that allow to structure complex multi-level mathematical models. Parallel analytics distributes workloads for data analysis, across multiple nodes in a server cluster, rather than addressing a large problem on a single supernode. The algorithms run on each node, processing a subset of the data. When processing is complete, or whenever required, datasets are aggregated, or rejoined, to generate collective information. There are many advantages of the asynchronous parallel approach. Less time to get information. By putting multiple nodes to work on the same problem, you can get insights from the data much more quickly than would be possible by running an analytics application on a single supernode with linear processing. This is a huge benefit when you want to get quick responses from massive amounts of data, and asynchronous processing allows to produce information that can be stored in memory until it is required by some subproblem. This speeds up the solution. In addition, it requires less demand for resources, avoiding congestion in computer systems. Distributed analytics is based on parallel analytics, and it is the distribution of the mathematical modeling process in many agents that act simultaneous and independently when they received information from its exogenous environment. The process can be summarized in the following steps. From a top-down process analysis, it is possible to construct mathematical or logical rules of interaction between multiple agents, representing each one a part of the system. Jointly, all the agents can represent the state of the reality. Starting from math, or logic rules, following an approach bottom-up, it is possible to build segmented, or atomized, models of the real world. Using asynchronous parallel processing, it is possible to define the simultaneous actions of all agents that keep on the right path a cyber-physical system. This processing is different from the traditional one, based on the synchronized use of mathematical models that are executed periodically. Autonomous real-time distributed optimization. Mathematically, this process may be supported by large-scale optimization algorithms, aimed at solving very large optimization mathematical problems, based on the intensive use of methodologies for partitioning and decomposition of systems. New technologies and big data shift from traditional optimization based on synchronized moments, to modern optimization, based on real-time events, in which models will run autonomously, when necessary, by events. Autonomous real-time distributed analytics is a topic open to researchers in advanced analytics. Artificial brains is a disruptive modeling methodologies for Industry 4.0, based on the integration of artificial intelligence and mathematical programming. The artificial brains corresponds to the scientific foundations, more specifically mathematical fundamentals, that allow to connect multiple mathematical models, algorithms or robots, exchanging information between them to obtain a common goal, and act as holistic intelligence of the organizations, or parts therein. Like the human brain, the artificial brain is composed of the following artificial components: neocortex, hypothalamus, and hippocampus. This evolution may be summarized as the shift from artificial intelligence to augmented artificial intelligence, that evolves from artificial intelligence very powerful in pattern recognition, to intelligence that powers the human brain, becoming an exobrain with high decision-making capacity, in real time, and autonomously. The decision support systems, DSS, were conceptualized as a set of mathematical models that exchange information between them, working offline. The artificial brain is the evolution of DSS under the Industry 4.0 revolution, that is conceptualized as a set of mathematical models that exchange autonomously information between them, working online, using distributed optimization. When all the models that make up a company are solved using the concepts of real-time distributed optimization, an artificial hypothalamus is obtained. This is how the human brain faces reality, using multiple models of reality, acting permanently in parallel, to make decisions. So, the artificial hypothalamus, a part of the artificial brain, is the algorithm that control the workflow of the models of the decision support system. It includes a general math language between algorithms that guarantees that the system is in the optimal path. This is based on the duality theory. In real-time and uncertain systems, the concept of an optimal point must be replaced by that of optimal path, as the one who is always close to the ideal optimal points. Algorithms swarm if large-scale multi-level optimization methodologies, based partitioning and decomposition of systems, are applied to get the smallest atom of a dynamic stochastic, the number of algorithms they generate could become countless. If parallel processing technologies, such as microservices, are used, the solution of a mathematical problem would be carried out by a swarm of algorithms that work autonomously and permanently to achieve the goal proposed by the decision maker. This algorithm swarm approach is currently used in artificial intelligence to manage swarms of robots, but the rules that robots follow are simple, logical and intuitive, and have no solid mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a multi-level sparse matrix, and whose communication protocol is governed by mathematical laws aimed at obtaining team results. The algorithm that simulates the hypothalamus is assembled by Optex, the HI's artificial intelligence, to generate mathematical programming solutions, using the models that traditionally make up a decision support system. Artificial brains are backed by the technological capacity of computing. It is traditional to associate mathematical modeling with large-scale computing, which today is linked to cloud computing, integrated by supercomputers of bits, and by the birth of quantum computers, which are the beginning of a new era. The current state of the computer technologies involves the integration of edge computing and cloud computing to implement systems with multiple highly complex mathematical models that can be run in parallel. Finally, there are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until, in the visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied. In 1972. In the book Human Problem Solving, wrote by Alan Newell and Herbert Simon. Thank you very much for your attention.